Projectile motion. You all have experienced projectile motion in your life. Anytime you throw something, that is projectile motion. So projectile motion is an extension to 2 dimensions of the free fall motion that we talked about last week. A projectile is any object that moves in 2 dimensions under the influence of gravity and nothing else. So as long as we can neglect air resistance, any projectile will essentially follow an arched path, a similar curved path. As it leaves the ground, it reaches a maximum height and then it falls back towards the ground again. Here we have a similar theme, that the horizontal and vertical components of an object undergoing projectile motion are independent of each other. That means that we have to treat the x component of the projectile motion separately from the y component of the projectile motion. So we'll use similar equations, but we use them separately for motion in the x and motion in the y. And so this little video that you see here is an example of a trebuchet, which throws objects to execute projectile motion. So a trebuchet is, it has a French name, is a type of catapult that uses the swinging arm here to throw a projectile. It's a powerful siege engine that was used in war up until the advent of gunpowder. So you have this little arm that you pull back and you put something in the end of it that's heavy, or you can light it on fire, and then you let it go and it launches an object through the air and will hit your enemy on the other side. And so I was talking about this concept of independence of motion. So let's think about this conceptual question right here. So we have a red ball right here, and it's released from rest 2 meters above a flat horizontal surface. And then at exactly the same time, we have a yellow ball with the same mass, and it's fired horizontally at 3 meters per second. We want to know which ball hits the ground first. Your instincts might be to say, maybe the one that's falling straight down, the red one, would hit the ground first. But remember that the motion in the y direction and the motion in the x direction are independent of each other. So this ball had no velocity in the x direction to start with. This ball, the yellow one, did have a velocity in the x direction to start with, but they both have 0 velocity in the y direction to start with, okay? And so if we're just thinking about motion in the y direction, and this thing has to fall to the ground, and the only acceleration it's experiencing at all is acceleration in the y direction, that means that they both have to hit the ground at exactly the same time. And so we can see that if we do this experiment and take stop motion pictures of it. So we drop the red ball and we release the yellow ball with some horizontal velocity here, and take a picture of where these balls are at exactly the same time stamp. And so you see that the red ball and the yellow ball both fall to the ground at exactly the same time. Of course, the yellow ball lands further from where it started in the x direction, but this is a good example of independent motion, independence of motion. So the vertical motion of these things are identical. The vertical motion of the yellow ball is not affected by the fact that it's moving horizontally. Independence of motion. Now here's a diagram of the velocity components of an object undergoing projectile motion. So this object is released from the ground, launched from the ground with a velocity at some angle with respect to the horizontal, okay? We see that it rises through the air, it eventually reaches its maximum height, and then it falls back down to the ground again, okay? And so the thing that you notice are these vectors. So the purple vector here, that's the total velocity vector. And then the orange vertical vectors, that's the component of that velocity, the total velocity vector in the y direction. And then the blue is the component of the velocity vector in the x direction. Okay, and so whenever the ball is, or whatever it is initially launched with some velocity above the horizontal, as it's rising toward the top of its trajectory, the y component of that velocity diminishes. That's just the same thing that we saw when we tossed an object straight up and then it falls straight down. The y component of that velocity decreases until it reaches its maximum height, and then the y component of the velocity becomes 0 when that object reaches its maximum height. That's important. The y component of that object becomes 0 at its maximum height. But the horizontal component remains non-zero, okay? See that the horizontal component, the component of that velocity in the x direction, is not 0 because it's still moving forward, okay? And then it starts falling back towards the ground, and as it falls back toward the ground, it's going to be accelerating back towards the ground, so the y component of that velocity gets larger and larger and larger. And this whole time, we see that the length of the x component of velocity, the x component of the velocity vector, doesn't change at all. It's the same. The x component of the velocity of this object is the same from when it was launched to when it's up here at its maximum height to when it's back down on the ground. Why? Because this object does not have any acceleration in the x direction. It is only experiencing acceleration in the y direction. So the x component of the velocity will remain the same the entire time it's flying through the air, assuming there's no air resistance and assuming there's no like rocket strapped onto this object. Okay, so that's important. Those are important concepts to keep in mind. So the equations that we can use for projectile motion, what are those? So we have them right here. So we take those same equations that we use for motion in one dimension, okay, in the x direction, and then we also at the same time use those same equations to figure out motion in the y direction, okay? So equations of motion for constant acceleration, you've already seen these before. You use the same set of equations in both the x and the y direction. So anytime you see an x here, you could swap it out for a y, and remember that those velocities are in the y direction instead of the x direction, and then you could still solve the problem, treating the x and the y components of motion separately. So then our kinematic equations for horizontal and vertical motion together become, well, remember when our object is executing projectile motion, it has no acceleration in the x direction, only in the y direction. So in the x direction, our acceleration will always be 0. So anywhere you see these equations, if you're thinking about motion in the horizontal direction for a projectile, then the acceleration is always 0. So some of these equations simplify here. And then we remember that the x component of the velocity is always constant, okay? And then for our vertical motion, we always assume that our acceleration is minus 9.8 meters per second squared. That's the acceleration due to gravity, okay? And then we take these same equations, but in the y direction, and just repeat them here. A key point is that our velocity, our initial velocity, is going to have some angle with respect to the horizontal axis. And so what you're going to have to do is break down that initial velocity into its x and y components. So you use the x component of the initial velocity up here for horizontal motion, and you use the y component of your initial velocity for motion in the y direction. And I'll show you in an example that I'm going to work through next how you can calculate the x and y components of your initial velocity in projectile motion when you're kind of leaving the ground at some angle with respect to the horizontal. But if you're leaving the ground with respect to the horizontal at some angle, the x component of that initial velocity is the magnitude of your initial velocity times cosine of the angle at which you're leaving the ground with. And then the y component is the magnitude of that initial velocity times sine of the angle at which you're leaving the ground with. So here we're going to practice those ideas with a fairly classic problem in physics that we use to model projectile motion. We have a long jumper that leaves the ground at an angle of 20 degrees with respect to the horizontal at a speed of 11 meters per second. And we're going to find how long it takes for this long jumper to reach her maximum height. We're going to figure out what is that maximum height and how far she jumps in the horizontal direction.
Now, in this problem, we have a long jumper, and that long jumper leaves the ground at an angle of 20 degrees to the horizontal. So here I have the ground. This is the trajectory that our long jumper takes as they leap through the air. Now, it is highly exaggerated compared to what it would actually be in real life. And it says that this long jumper leaves at an angle of 20 degrees to the horizontal. So that means I am here at the horizontal and I go up 20 degrees. And so my velocity vector, my initial velocity vector, looks like this, okay? And then this angle in here is my 20 degrees, all right? And then this velocity vector has a magnitude of 11 meters per second. So V0 is 11 meters per second. Okay, well, that's hard to see here. Let's write it again. Equals 11 meters per second. Okay, now, in order to solve this problem, we're going to work through a bunch of different steps, answering a couple of different things. The first thing that we're going to do is figure out how long it takes for the long jumper to reach maximum height. So maximum height up here, which I'm going to call Y max. Okay, we don't know what that is. We're eventually going to find that. But the first thing we want to solve for is how long it takes for the long jumper to reach here. So maybe I'll call it T max equals question mark. Okay? The thing to remember whenever you're executing projectile motion is that if you're traveling horizontally, whenever you reach the apex or the maximum height of your jump or your path, that the y component there becomes 0, the y component of velocity. So right here, we have only horizontal motion at that very instant and no vertical motion because we don't go up or down anymore past right at this point, okay? So right at that point, we have Vy equals 0 meters per second. But the horizontal component of velocity is non-zero at that point, okay? Now, we will use this information in order to find how long it takes for the long jumper to reach this point right here. So let's start with this equation right here. Vy is equal to the initial vertical velocity plus the acceleration in the y direction times time. Okay, now our velocity, whenever we reach the apex here, the top of our jump, that's 0. That's the Vy right here in this part of our problem. So that's 0. 0 equals. Okay, now what is our initial y component of velocity, V0 y here? To figure out the initial y component of our velocity, we need to go back over here to our diagram. Okay, so here at our diagram, we've got that the magnitude of the initial velocity is 11 meters per second. Okay, that's the magnitude of this vector right here. But we need to break that down into its x and its y components. Okay, so here I just drew in a little triangle, a right angle triangle here. This angle right here is our 20-degree angle at which we leave the ground. This component, the vertical component of that vector, we're going to call that V0 y. Okay, that's what we need for right here, right? So if we appeal to trigonometry, we know that sine theta, that's our angle theta here, is equal to opposite, which would be V0 y, over hypotenuse, which is our 11 meters per second, okay, or V0, the magnitude of that, okay? So then the y component initially of our velocity is going to be v naught sine theta, okay? And so over here, my y component of my velocity is going to be v naught sine theta, and my y component of acceleration is always going to be minus 9.8 meters per second squared. That's our acceleration due to gravity. So this is going to be minus, I'm just going to call that g, okay? So, because just 9.8 meters per second squared on its own is what we call g. So minus g times t, all right? So we want to solve this for t because we want to find how long it takes us to get right there. I'm going to add gt to the other side. We're solving for t, so I'm going to divide both sides by g. So then t is equal to v naught sine theta over g, okay? And so then that's going to be 11 meters per second times sine of 20 degrees divided by 9.8 meters per second squared, okay? And so then time is equal to 0.384 seconds. So the time to our maximum height of our jump is 0.384 seconds. All right. And so for part B, we are going to be asked to find what is the maximum height of the jump. So we're going to find now y max, okay? So I'm going to use an equation that will help me figure out the vertical component of my displacement. And so I'm going to use this equation right here. Y is equal to y0, y naught, plus v naught y t plus 1/2 acceleration in the y direction t squared. Okay, so we can say that right here at the ground, y naught, where we're starting from, is 0. We start from 0 meters. This, our final y height, our maximum y height, is what we're solving for. Our initial y component, we already calculated. We've got that right there. And we know what the acceleration due to gravity is, and we know how long it takes us to get there. Great, so we know everything. So this is going to be v naught sine theta times time plus 1/2 acceleration in the y direction, t squared. Okay, so that's equal to 11 meters per second times sine of 20 degrees times our time here, 0.384 seconds, okay, plus 1/2 times our acceleration in the y direction is minus 9.8 meters per second squared times time squared, so 0.384 seconds squared, okay? So if you plug all that in, this first term right here, this first term is 1.445 meters. Okay. The second term here is going to be negative because of that minus sign on the acceleration in the vertical direction. And that's going to be minus 0.722 meters for this whole segment right here. Okay. And then we subtract that off of the 1.445 meters, and then we get that the maximum height is 0.772 meters. All right, 0.722 meters. So it should be 0.722 meters, not 0.772 meters. Sorry. There we go. And finally, for part C, how far does our long jumper jump? We want to find this total distance right here. Okay, so if we say the x naught is right here, what we're looking for over here is x final. How far does she jump? Sometimes we also call this the range, sometimes represented by capital R. Range is how far in the horizontal direction you are displaced from your initial position when you're executing projectile motion. So we're going to find how far she jumped from her initial starting point. So we're looking for an x position. So I'll start here with x equals x naught plus v sub naught xt plus 1/2 ax t squared. Okay. Now remember, in the horizontal direction, that's this direction, we have no acceleration. We only have acceleration in the vertical direction here when we're executing projectile motion. So the acceleration in the horizontal direction is 0. We're starting from a place that we're going to call x equals 0 here. So our x sub naught initial x position is 0 meters. So then our horizontal distance that we've jumped from our initial starting point, x is equal to v naught x times time. Okay, we know the time. We still have to get this horizontal component of the velocity, of our initial velocity. Come back over here, and the same way that we found the vertical component of the initial velocity, here my angle theta, here I have my initial velocity vector. So the horizontal component of my initial velocity vector is this one that I drew in right here, v naught x. And so if we invoke again trigonometry, we've got this side here, v naught x, is adjacent to our angle of 20 degrees here. So adjacent side, we're going to say cosine theta is equal to my adjacent side, which is the x component of my initial velocity, divided by the hypotenuse, which would be v naught. So v naught x is equal to v naught cosine theta. All right, so over here, our range is going to equal v naught cosine theta times t. So that's going to be 11 meters per second cosine 20 degrees times, there we go. Oh, no, we can't use this time here to get our horizontal distance that we've jumped away from our initial starting point, because remember that this time was the time to the apex, the maximum jump, okay? Maximum y height of her jump. Now, the cool thing about projectile motion is that as long as we're not applying an additional force in the horizontal direction, the time it takes you to reach the apex of your jump is the same amount of time that it takes you to fall back down to the ground, okay? So this time, this is going to be the total time, okay, from jump all the way up and then back down to the ground again. And so that total time is going to be twice our 0.384 seconds. So this is going to be 2 times 0.384 seconds, okay? So we plug that into our handy calculator, and we get that the distance she jumps away from her starting point is 7.94 meters. And again, this horizontal jump away from the starting point is sometimes referred to as the range as well. And so using our equations for kinematics in 2 dimensions, treating the x and the y components of motion separately, we're able to find the time it takes to get to our maximum height, what that maximum height is of the jump, and how far we jump from our initial starting point.